Okay, in this problem, Dakota lives 1,500 meters from school. So, right, we have our school here. This is our school. Looks a lot like a house, I guess. Okay, well, that's our school. And we live a certain distance away, right? We live 1,500 meters. So maybe as a straight line, we could draw a distance. Let's say that this is where Dakota lives, 1,500 meters away. So we're dealing with a distance problem here. And that distance is, just to be clear, 1,500 meters. I often do this. I often like to draw out the problem before I even solve it. Just keeps my mind from wandering. I have a tendency to wander off and think about all sorts of things. So if I draw it out, it kind of keeps me focused about the problem. Now that I have a visual, as simple as this problem, the premise of this problem is, I can at least think back to this and help myself focus. That's just a little trick that I use. Here, she leaves for school walking at a speed of 60 meters per minute. So, right, the rate as we walk is 60 meters for every 1 minute that passes. Okay, write an equation for her distance d in meters from school after she walks for t minutes. So I've said this before, but if you have a problem here with the variables and that's kind of throwing you off or tripping you up, try to draw a picture or substitute actual values to understand what's happening. So let's just be clear about our variables for a moment. We have d, which equals distance, not traveled, but from school. Let's think about that for a moment. That's a key step here. If Dakota walks a little bit, like starts off here, and then after a minute, let's say, walks about this far, 60 meters, right? What has happened to her distance from school? Well, initially she was 1,500 meters away. Now she's, well, after this, if this distance is 1 minute, and she's walking 60 meters for every minute, well, then there are 1,440 meters left, right? I just take the 60 meters from the total distance because every minute she's getting 60 meters closer. You want to think about that in this problem. So our distance from school is going to decrease over time, right? Assuming nothing else happens, but minute after minute, she'll walk closer and closer to school, and that distance between her and school will lessen. And t is equal to time in minutes. And let's just, again, if you're having a hard time thinking about this problem, set up maybe a simple table. We have t, time, and d, distance from school, and then plug in some values to see what's happening, right? So let's say 0 minutes have passed. Well, that means she hasn't left yet, and she's 1,500 meters away from school. After 1 minute, though, right, we'll be 1,440 meters away, or 60 meters left. After 2 minutes, we'll be 1,380, right? Take another 60 away. After 3 minutes, we'll be 1,320 meters away, and so forth. And what you can see is that the distance from school, right, is going to be equal to the starting point, 1,500, minus 60 meters for every minute, t. In other words, we just subtract 60 meters times the amount of minutes from 1,500, because we thought of it here one step after another, right? 60 and then subtract 60 and subtract 60. But this equation, what it's doing is saying, okay, after 2 minutes, how many meters will she be from school? Well, you can think of this as 1,500 minus 120, or minus 62 times, which is what this part of the equation would do if t was equal to 2, right? Because we can show that it's just 1,500 minus 60 times 2. So that means 1,500 minus 260s, or minus 120, which is 1,380, our distance from school. So it's a nice way to relate this, and in terms of a graph, you always want to think about the equation table and graph here. You can think, okay, well, here my distance from school is my dependent variable, right? Distance from school, because that depends on how much time has passed, right, and the rate at which she's walking. So at 0, we're at 1,500, way up there, right? My scale here is terrible. I'm going to go up by 500, 500, 1,000, 1,500. After 1 minute, she's at 1,440, barely noticeable. 2 minutes, 1,380, right? And so forth. And you get this line, probably more like that. right? It just keeps going until it reaches 0. And my line is almost horizontal, just because of my scale, right? And you can ask, well, how long would it take for her to reach school? We can use that equation. So that means that D equals what? Well, when she reaches school, D equals 0. So how long will it take for this line to reach 0? How many minutes? Just plug it into your equation. 0 equals 1500 minus 60t. So to solve for t, I would add 60t to both sides. I just want to turn that into a positive and get my variable all on one side. These cancel out. We have 60t is equal to 1500 divided by 60 on both sides, right? And that's what t is going to be equal to. How many times does 60 go into 1500? Well, I know that 60 times 20, right, based on 60 times 2 equals 120. So 60 times 20 equals 1200. So 60 goes into 1500 at least 20 times, plus, well, there's still 300 left. And I know that 60 times 5 equals 300. So it's 25 times, or 25 minutes. So here on my x scale, right, this is 1 minute and 2 minute, 3 minute, 4 minute, 5 minute, 6 minute, 7 minute, 8 minute, maybe 20, 25, say estimating about here is when she'd reach school. So my line should have a slope a little bit more like this, right? That might be a little bit more accurate. Sorry about the background mess here. It's just, playing with slope and playing with these equations and lines might help you really develop a wonderful sense of them. So again, always look at the table, graph, and equation, at least even if you're doing a rough sketch, to give you a sense of, is this making sense? Is this working out the way that I imagine it would? Don't lose your intuition. Don't just start plugging in equations. Always think about it. Thanks.